Okay, off we go. So real quick before we get back into the math, don't forget there's an exam on Monday. Summer moves blindingly fast, so here we are already. As I indicated on the schedule, the class schedule, the last fair game section is the section we're currently in, but just sort of the part one. And just to be clear, that's everything before we get to the page we're looking at on the screen right now. So all of what I'm going to call regular change of variables is fair game. Coordinate system change of variables, not fair game. And then there's sort of after coordinate systems, I have another sort of a third part of 5.5, or what I lump in with 5.5, which is symmetry theorems. That's also not fair game. Okay, all right. So off we go. We talked about some of this last time, and let's focus on polar coordinates here because that's what we're going to delve into more deeply first. Here is what I'm going to call the polar coordinate conversion function, or you might just call it the polar coordinates function. It's not good. Bog down the name. And the big observation is that it is a change of variables function too, because it's got two variables in, two variables out. It's something we can pull back through. We've already computed the stretching factor, right? Or why don't I highlight it here? And specifically, we've seen that in order to be able to enjoy this luxury of not having to deal with the absolute values, it does come with a cost that we're only allowed to use non-negative values of R. So you got to follow that rule at this point. Otherwise, you owe absolute values, and I don't think anybody wants to do that. Okay. All right, so let's see this in action. We did something analogous with cylindrical and spherical. We'll come back to those in a bit. So here it is in action. We're going to look at the first quadrant portion of the unit disk. That's this region right here. And over that, we want to compute this integral. Right? And we're going to do a pullback, and there's some algebra to be done with the pullback. We'll get to that in a minute. But keep in mind, when you do a pullback, the big idea is you need to find the pullback domain. In other words, you need to find a domain in the R theta space whose image is exactly the original domain. Okay. So I claim that pullback domain is this region right here. It's this rectangle. Now let's think it through. How do I know that that's true? Let's look at one edge at a time. Let's think about this edge right here. Notice that edge is on theta equals 0, and it goes from R equals 0 to R equals 1. Well, here's the thing. I know exactly what that is in the XY plane. It's just those points. And now let's go to the next edge. What about that edge? Well, let's see here. That's on R equals 1, and theta goes from 0 to pi over 2. That's what that is. Everybody with me? Okay. Let's see here. We can look at this edge. Well, let's see. Theta is pi over 2. R goes from 0 to 1. That's this. And the weird one, this edge, now that edge there, that left edge of our proposed rectangular pullback domain, R is 0 for all of those points. And R equals 0. I don't care what theta is, all of R equals 0 goes to the origin in the XY plane. So there's a weird thing sort of geometrically happening here. It's like, sure, things are being distorted and kind of bent, etc., but among other things, the entire theta axis is being sort of pinched down to a single point right there. So that's just kind of what the polar coordinates function does. Anyway, but the punchline is you can imagine that since those edges correspond, then everything inside here goes to, well, inside here. Is that cool? Everybody buying it? Okay. And it's all over but the shouting. then, because we got our pullback domain. Our pullback domain is easy to describe. The range of values of r and theta, here they are. Right? This area in the xy plane relates to area in the r theta plane by way of the stretching factor. There's our stretching factor. Stick that in there. The easiest thing to forget. It's the biggest whoopsie in all of change of variables, is accidentally forgetting your stretching factor. So don't forget that. I'll be warning you about that more and more. And then plug in. And the plugging in is, that's the easy part of the pullback. X is r cosine theta, y is r sine theta. We get to use all of our old formulas for polar coordinate conversion. And x squared plus y squared is r squared. So we've done the pullback now. We have a new integral. So we wanted to compute this. We are instead going to compute this. It has constant bounds. That makes it relatively easy to do, and again, all over but the shouting. You take the antiderivative, you plug in, blah, blah, blah. Everybody good? Okay. Was this worth it? Well, let's consider the alternative. The alternative is to take this region and write it out. Now, arbitrarily, I slice here with dy dx. And notice I get square roots in my inner bounds, which means I'm going to have square roots in my outer integrand, and it's not the... I don't really like this integral. I could do it, right? But it's significant effort in this case, involving, I think, looks like it's probably going to involve a trig substitution. Y'all know how to do trig substitutions? Some of you might not know, but experience shows that many Math219 students don't know how to do trig substitutions. If that's the case, I do think it's a good technique. I strongly encourage you to look it up. I have my own take on it. It's in the Miscellaneous Topics playlist on my YouTube channel. It's a 30-minute discussion that is everything that I would dream that my students would know about trig substitutions. Honestly, if you watch the first 10 minutes, you'd probably be okay. So anyway, good thing to know. Okay, so big win. And it's literally a change of variables. We literally did a pullback. Now, the next observation I want to make is kind of just a way of thinking about things. And I'm just going to start by observing that theta slices, we can actually see them in the xy plane. And what I mean by that is, let's think about an actual theta slice. Keep in mind, when we say slice, we mean perpendicular to that axis. So there's a theta slice, and I make the simple observation that when you do a theta slice perpendicular to that axis, said differently, you're looking at a constant value of that variable. So a constant value of theta. And here's what a constant value of theta looks like in the xy plane. So the way I want to say it is, yeah, there is a slicing process that's happening over here in our theta space, but I can see it happening here in the xy plane. And what we're going to find momentarily is that if everything you're doing over there you can see over here, you don't even need to draw what's happening over there. This is a nice little bypass. But you can sort of sidestep and not draw the pullback domain. Now, this is literally exactly the same picture we had on the previous page. I've just kind of scratched out this part just to show that we don't need it. Right? So here we go. I have an integral, same domain, and I want to talk about doing this in polar coordinates. There is a pullback domain. I could draw it. There it is, but again, we're going to not look at it. And let's just try to figure, without looking over here, what does this process of doing theta slices over there look like? And well, what it looks like is this. These are our various theta slices that we're taking. And I can see clear as day right here, for example, that first slice is at theta equals 0, because that's I mean, that's how polar coordinates work. That's the theta equals 0 line, right? So boom. I don't need to draw that over here. I can also see that as my slicing progresses, right, my last slice is going to be that one right there. I don't need to draw it over here to see what theta is on that last slice. I can just, I know how polar coordinates works, and that direction in the xy plane, that direction is where theta is pi over 2. So I didn't need to draw any of this. It's just a slick observation, and then, by the way, we can keep going, looking at a particular theta slice, right? Yes, I suppose I could point out that the first value of r is there, but I can also see right here, there it is, and it's clearly r equals 0. And likewise, the last r value, whoops, I wanted that to be the darker, here we go. Last r value is there, and there it is, and I can see clear as day because it's a unit disk, and that's where r equals 1. So we don't need to draw what's happening over here at all. This is what people mostly mean when they say doing an integral in polar coordinates. What they mean is, okay, there's actually a change of variables underneath it all, but in terms of how you break it down, it consists of these, just a handful of steps. Convert the integrand. Don't forget your stretching factor. Little doff of the cap to the fact that this is, in fact, a change of variables. So you got to have your stretching factor in there. And then just determine your bounds. All of these bounds you determine by doing polar slicing. In the of the domain that was presented to you in the first place. Just slice it up in this polar sense. It's all examples from here on out. That's pretty much how it works. It's just a special case of change of variables. By the way, there are different ways to think about this, and that's fine. I find this to be the most satisfying one myself. I think the book gives a slightly different take. Certainly many books give significantly different takes on how to think about doing integrals in polar coordinates. You're very welcome to look at those. I think this one's ultimately the easiest, because all of the heavy lifting, where did this factor of r come from? We're just piggybacking off the stuff we already knew. And we already knew about change of variables and stretching factors. So why reinvent the wheel? Okay, another example. Here our domain is the entire unit disk. By the way, this is an example that allows us to walk away with a very convenient generality. But let's do the example first, and let's think about how we slice this up. Our first slice, I guess you can kind of start anywhere you want, but I'm going to start there where theta is equal to 0 because that's convenient. Right? And then, let's see here. Let me color code a little better. I'll do theta equals 0. Do it like that. So as theta increases, right, theta kind of goes all the way around, if you will. And just to be consistent, as theta continues to go around, theta gets bigger and bigger. By the time I get back to where I was in the first place, in other words, by the time I'm done describing my domain, we've made a full turn, and theta has made its way, therefore, up to 2 pi. Now, you got to be careful. These are in the same direction. Keep in mind, this is just a kind of a convenient, geometric hack for determining bounds. The reality is there is a pullback, and in that pullback, you got to be consistent. If you keep going, if theta keeps increasing, it can't increase to what it started as, right? So we got to call this output, this ending value 2 pi. We can't call it 0 again. So the upper bound is 2 pi. So our theta bounds 0 to 2 pi. Everybody good? Yeah. Correct. We're not taking any negative r's here. So, it's tempting to say, well, what about points here, right? Well, I'm going to get this point when theta is that way. And if theta is like this, then I get to those points with positive r's. Now, I could, let me mark this up. So, like a point here comes from theta being like that, and then r is going to be, positive, whatever that distance is. You are right. I could have viewed that as this value of theta, at which point then I would have a negative r. That's true, but that's not what we're doing, right? So you'll notice in particular that while theta is allowed to be this value, while theta is allowed to be that value, we've specifically got r going only 0 to 1. So I end up only, for that theta, I get only those points. And the point in question, right, this point over here comes about for a positive value of r for the other theta. Does that make sense? Mm-hmm. Yeah. Yes?
If you were to allow for negative r's, you would have 0 to pi and then negative 1 to 1 pi.
And then you'd have an absolute value in your integrand, and I think it would be just completely unjustifiably inconvenient to do that. But yeah, totally. Right. But please don't. Right? Because dealing with the absolute value, oh gosh, it can be confusing, and it's just a wrong answer machine. Right? So we definitely don't want to do that. Yeah. Everybody good? Okay, moving along. Just to be helpful, point out some tips and tricks. I have never encountered an example in which this is not the best way to order your differentials. Correction, let me say, I have never organically, naturally, encountered such an example. Now I have, just for the challenge of it all, I have constructed examples where it's better to do it the other way, but it was a weird, unnatural example it's not likely at all to come up. So I'm going to say just always do it that way. And I don't think you're ever going to have a bad experience if you just always do it that way. Okay, here's another little helpful tip. Something that's very easy to mess up is to spend all your time thinking about, the ranges of values and the slices and the starting and the ending of R, and worried so much about all of this that the stretching factor can be forgotten. I've seen it happen 1,000,000 times. And it's a really big deal. I mean, if you think about it, that factor of R, the stretching factor there, that's the only part of this process that isn't just kind of plug it in, right? So it's a really big deal. On an exam, if this were an exam question, for example, having the correct stretching factor in there, depending on what else is going on in the question, it could be 4 or 5 points. It's a big deal. Now, if you forget it, again, I have to grade on the basis of what's written, and I cannot distinguish those who totally know and just whoopsied from students who don't know that something needs to go there, right? So it's a tragedy. It's a real tragedy, and I don't want this to happen to any of y'all. So my best solution to how to advise you to make sure that you don't accidentally just whoopsie yourself out of 4 or 5 points, right, is do what I do and always write the entire DA, right, the stretching factor and the pullback differentials, RD theta, write the whole thing down all at once. If you build a habit where you never write down DRD theta by themselves, always write down RD theta, you're going to need that R anyway. You will never need DRD theta without that R in there also. So just always write it down all at once. And if you hold yourself to that rule, build the habit where you just always write the whole thing down all at once, it'll be a lot harder for you to accidentally forget. And again, tragic error of forgetting something critical. Does that make sense? Okay. It's just a suggestion. You don't have to, but that's the reality. And then again, as usual, we find bounds by looking at the relevant key points, identifying what curves they're on, writing down their equations, and then solving to get the bounds you're looking for. So let's see more examples. This is a weird one. Here we have as our domain this annulus. It's the part inside the outer circle, but outside the inner circle. Like so. Yeah. Weird domain. Could happen. I like to think of this as a moat. I don't know why, I just find that fun. And so you got your castle in the middle, and this is the moat going around it. And maybe you want to compute how much water is in the moat. Maybe you know the depth of the water as relates to the distance from the center of the castle, perhaps. It's not a crazy scenario. So, okay, well, how do you do this? Now, it is tempting to say that we're going to look at an integral over this whole disk and then subtract the integral over the inner disk, green minus purple. Tempting. Here's the problem. You can't do that, and the reason you can't do that is because our integrand has a singularity there at the origin. The integrand's not defined there, and we do not have any working way to handle this idea of an integral on a domain where the integrals go to serious singularity. This is not a little micro, right? There's a real problem there. And now y'all may be thinking, we'll use an improper integral. Well, how do you define multivariable improper integrals? And there's sticky issues there, and it's not. We're not going to go down that road. So basically, I'm going to call this a dead end. You can't do it that way. So what else might we do? Well, I suppose we could break this up into 4 pieces, like so. 4 separate pieces. Here's the thing. Each one of those is a hard integral, and there's 4 of them. And I say each one's a hard integral because each one has part of its boundary comes from a circle. At least part of its boundary, maybe 2 parts of its boundary come from a circle, which means there's square roots all over the bounds, which means there's square roots all over the outside integrands, which means they're hard integrals. Right, so this is a bummer approach. Yeah, I don't think you want to do that either. So, good news, of course, it's a very easy integral in polar coordinates. So no big deal. We start where theta is equal to 0. We go all the way around to where theta, of course, is 2 pi. By the way, that was the big takeaway from that previous example we saw. If your domain surrounds the origin, theta is going to be 0 to 2 pi. So you don't have to sort of reinvent the wheel on that every time. Just if it surrounds the origin, theta goes 0 to 2 pi. And then, for a given value of theta, R starts at that point, which is on that curve, which has that equation, among others, right? We could write it rectangular coordinates, but that is the relevant equation in which I solve for R to get my lower bound. And likewise, there's the last point. It's on that curve that has that equation, which I can solve easily again, and gives me that upper bound. So nice and easy peasy, nothing to it. Super easy integral, as it turns out, and boom, we're done. We just saved ourselves loads of trouble. Everybody happy? Okay, here's a little bit trickier one. here we're looking at part of one disk that is outside of another disk. Now, I want y'all to take some time to make sure you're comfortable with the suggestion that this is that disk and this is that disk, and that if oh, by the way, this notation here, that purple backslash, just says remove everything from the set on the left that is also in the set on the right. It basically says, minus. It's like, throw away all the red. And so what we end up with is this gray region right here. Okay, so make sure you're comfortable with that. Notice the notation, that kind of notation we will use in the course on exams, etc. So make sure you see how to understand that geometrically. And how are we going to do this? Well, we got theta slices, right? Theta, kind of like so. And I got to think about my start and my end. Oh, by the way, before I forget about it, notice RD theta. Write that down all at once. Right? Don't forget the R. R is critical. Right? Okay, so theta is going to start at that point and end at that point. How do I determine that value of theta? There's a couple ways you can do it. The sort of obvious way to do it is to notice it's on that curve with that equation, and it is also on that curve, which, let's see here, which kind of has, you might say that equation, make that an equals instead of a less than or equals, which is in rectangular coordinates, which you could then convert to polar coordinates, which would give you this. Make sure you can do that. Okay. Remember, that's a flashback to chapter 1, late chapter 1. We talked about that kind of stuff. And okay, so we've got that the point we're interested in is on two curves with two equations in which I can solve for theta. And you will get that. Fine. Okay, so you can do that. Here's the slicker move, though. And I really like this. This is a really clever idea. I didn't think of this. Somebody showed me. So again, the question is not whether you're clever enough to notice the trick yourself. The question is whether you are able to make effective use of the trick after having been shown the trick. Right? So don't set the bar too high for yourself. So notice, so this right there is a radius of that circle. So is that one. We know the radius is 1, so that tells me those lengths are 1. And then we notice that this is a radius of that circle known to have a radius of 1, and so that's 1 as well. And so we have ourselves an equilateral triangle. We know angles on an equilateral triangle, and that tells me that this first, wrong color, this first theta slice at that point, the value of theta there is negative pi over 3. So just a nice little geometric hack. Comes up more than you'd expect. Nice little trick to have in your toolbox. Everybody happy with that? Okay, and then it's kind of all over with the shouting. So we've got range of values of theta. Theta slice looks like this. Our first value of r is there, which is on that curve with that equation. Easy to solve for r. Our last is there on this curve with that equation. Again, easy to solve for r. Everybody all right? Yeah.
How is R2 cos theta?
One more time.
The R, operating on the R.
Yep.
2 cos theta.
Yep.
How is it?
Yeah. Oh, yeah. So that again, that comes from this. Gosh, I just want to clean up the mess. So this curve, the first observation I would make about it is it comes from what I'm going to call this equation, right? And so you just have to convert that from rectangular coordinates to polar coordinates, and that's a chapter 1 thing. And when you take the polar conversion formulas and just plug them into here and see what it turns into, this is what it turns into. It's a good exercise to work that out. Back to 1.7. Yeah. Okay. All right. The last thing, of course, don't forget the plugging in, right? So we do have to convert the original integrand. The original integrand was just x, and easy to convert. That's just r cosine theta. So do notice that your new integrand is the original integrand combined with that stretching factor, right? That stretching factor is part of the deal. So our new integrand is r squared cosine theta. Yep.
So the theta line that comes out, is that from the origin to that line you're finding?
This, you talking about this right here?
Yeah, so it's from the origin to that line, the angle, that's that theta.
Yeah. Theta it's the usual theta, right? So theta is defined as you look at the positive part of the x-axis, go counterclockwise from there until you get to the direction you're describing. That's theta. Absolutely. And you do make a really good point. Theta is always measured as an angle from the origin. There is this easy, whoopsie kind of, it's a combination of wishful thinking and sloppiness, where students will just will compute their theta angles from the center of whatever is the most convenient round thing in the picture. That you do not do, right? So it's not this angle. That is not how theta is computed. It's got to be as measured from the center, because that's what theta is. Yeah. Is that satisfying to everybody? Yeah. Okay. Cool. This is a super fun example, and we're behind schedule. We don't have time, so I'm going to have to skip this one. I encourage you to take a look. It is actually really cool that we can compute this integral. Notice the integrand. We can't find an antiderivative of that integrand. This is one of these famously un-antidifferentiable. I don't know if that's the right word. Anyway, there is no antiderivative without using power series. Okay? But nevertheless, even without an antiderivative, we can compute the integral by a really clever trick. I mean, really, really clever. That's demonstrated here. And I encourage you to take a look, but you don't have to. It's not part of the course, but it's a very cool calculation. Sort of a historic level of cool calculation. All right. Let's do cylindrical coordinates. It's, oh my gosh, so the same. It's polar coordinates with a z, right? It's really the same. And so no surprise if we're in the pullback r theta z space and we want to talk about slices perpendicular to the theta axis. Well, here's a slice perpendicular to the theta axis, and it represents a constant value of theta. And we know what constant values of theta look like in XYZ space. So why bother messing around drawing a whole pullback when everything you need from that you can see right here? Same basic idea. Different geometry a little bit, but same basic idea. Again, don't forget your stretching factor. Good hack to not forget the stretching factor is always write all of this down all at once. You will never not need that R. When you're writing down dr d theta dz, you will always need that R. Why wait? Get those points, right, in the bank. And don't just assume that you'll remember, because, 20% of students whoopsie that. Okay. All right. Okay, which way should you slice? My experience, again, is that, and I don't want to say that these are always better than your other options, but I will say I've never seen organically an example where one or the other of these is not just as good as any other option. So said differently, I've never seen an instance in which it costs you anything to just keep your dr and your d theta together and in that order. And then the only question you should ask is whether you want DZ on the outside or DZ on the inside. If you keep it simple, right? Don't overcomplicate this. Just look at these two options. I don't think that will ever give you a disadvantage of any significance at all. Okay. And then the usual speech about where bounds come from. Okay, so again, let's just do one. Here you go. We're going to look at the upper half ball of radius A. So this is like a, it's like we had a ball center at the origin, and we cut it through the middle and let the bottom just fall off, and now we have this three-dimensional solid half ball. Okay. Now I'm going to start with my differentials in this order. No particular reason. In just a second, we'll do it the other way. But for now, let's focus on this. And one at a time, let's think about our theta slices. Well, that's how you do theta slices, as we discussed on the previous page. And the theta slice itself is like so. All right, now on that theta slice, I want to think about the range of values of r. So where does r start and where does r end? Well, that's where r equals 0. And as r increases, that will be my last r slice of our theta slice, right? That's the biggest r can get on this theta slice. So again, you get lucky sometimes. The fish just jump in the boat. The fact that this starting value of r is 0 is kind of a freebie, right? And then again, you get lucky other times as well. This point here, now we could write down the equation of the blah blah and do a bunch of algebra. Check it out. R in this case is literally a radius of this sphere of radius A, and so that means that at this point the radius is A. So upper bound for R, A. Everybody happy? Okay. All right, now for our R slice of our theta slice, looking at that, now we just have to think about the Z bounds. Z clearly starts at 0. Take your freebies when you get them. Z ends there. Here's where we are going to have to do a little bit of work. That point is on that sphere. That sphere has this cylindrical equation. Now let me recognize, very often we think of the equation of the sphere in rectangular terms. Spherical coordinates would be a nice way to do that as well. But here we're doing cylindrical coordinates. So think in terms of how you convert from either of those other forms to get this cylindrical form that we need, because we're doing things in cylindrical coordinates. Right? Reminder, we're looking for a value of, let's see, color choices. We're looking for a value of Z. So in this equation, I've got to solve for Z. And what I get is my upper Z bound. All good? Let's do it the other way. Now we're going to do our Z slicing first. A Z slice, of course, constant value of Z, nice horizontal slice there, and that's what they look like. Clearly starting where Z is 0, clearly ending at the top where the value of Z is also a radius. So A. Then we fix a Z. And we keep going. What does theta do on that Z slice? Well, it surrounds the Z axis, so I say it goes all the way around. All the way around means 0 to 2 pi. Is everybody still with me? Okay. And then, lastly, we got to think about our theta slice of our Z slice. And now I want to know, where does R start and end? Well, R starts there where R is obviously 0. So again, you get the, nice little freebie. Take them when you get them. And where it gets interesting, that point, the last value of r, that point is on this surface that again is the sphere that again has this equation. Now here's where students make another mistake. A lot of students will say, oh yeah, I already did that one. And the answer was square root of a squared minus r squared. Not anymore. It's not the same anymore. Because we are now looking for an r bound. We are no longer going to solve for z. We solve for the variable whose bound we're looking for. So now we're solving for r, and what we get is square root of a squared minus z squared. Not r. Is that cool? What advise it? Okay, nothing to it. Always write down RD theta dz all at once. Don't forget to insert your stretching factor as you're writing down your differentials. You're going to feel a compulsion to save yourself the time of, I don't want to write down the R just yet. That'll cost me a quarter of a second. I'm going to write down my differentials and focus on all this other stuff. That's how you forget. And then unavoidably have to lose points. Write it down first. Don't miss it out. Okay, spherical coordinates. Well, so again, with spherical coordinates, you can see what the slices look like. Now, the pictures are weirder here, but the main example really is that the theta slices look just like they did in cylindrical coordinates. That's the main observation we need to make. And I say this is the main observation we need to make because it's going to turn out we're always going to put our d thetas on the outside. Again, how you order the differentials among your 6 different choices of how to order those differentials. You should always put that on the outside. So you kind of don't really need to worry about all the rest of that. We'll just think about what happens when I slice up my theta slices. So again, this is the order. And I'm not saying that other orders won't ever be just as good. Sure, they might be. But I am saying that it is almost unheard of for this not to be just as good as any other ordering. So, and again, I could get into smart alecky mode, and I can construct examples where this is a bad choice, but it's unnatural and weird and hard and nothing you should worry about. So always do them in that order, and also further, in addition to putting those in that order, always write your stretching factor as you write down your differentials. Right? So you should memorize all of this together. Always write down all of this together. Rho squared sine phi d rho d theta should kind of fall out of your mouth all at once. That's what you memorize. That's what you mumble in your sleep, right? Again, if you don't, you're going to forget. It's a question of time. Why would you do that to yourselves? Okay. All right, so let's dive in. Here we go. Notice d rho d phi d theta. Notice, got my stretching factor already there. Okay. That means we're doing theta slices first. So, okay, back up to here. Here's how we do theta slices. We're completely surrounding the z-axis. So, theta goes 0 to 2 pi. Everybody happy? Okay. So, 0 to 2 pi. All right. Now, how we draw our theta slice. This is just a kind of a personal preference. I don't even always do it, but I think it's a good thing to maybe encourage yourself to do. Do keep in mind this is what the theta slice looks like, and that's fine, I suppose. This is literally that theta slice is like so. I personally like to redraw that sort of looking straight at it. I like to imagine this, if you will, sort of R-axis. right? And the advantage to redrawing your theta slice like this is that now you're looking right at it, and right angles look like right angles. Right? If you don't do this, you can still get by and it could still be okay, but notice that this right angle right here does not appear at a casual glance to be a right angle there. Now, depending on how good you are at thinking three-dimensionally, maybe you're just got that locked in, and this does look like a right angle to you because this R axis that I'm visualizing looks horizontal, and you're just but and sure, ideally in an ideal world you would be good at visualizing things, and I do my best, etc. But it's an opportunity for an illusion. Makes things a little bit more confusing. So you don't have to do this, but I think it's a healthy exercise to redraw and do your phi thinking from this picture. So now, don't forget, phi is measured from the origin, sort of leaning over from the vertical. And so, your phi slices look kind of like this. But it's just easier to see them like that. My opinion. Okay, so that said, our theta slice looks like this. And think about what happens to phi. Well, we're going to start there at the vertical where phi is equal to 0. And then we keep rotating on down, and these phi slices get shorter and shorter and shorter and shorter, and they never really quite go away. Let me just get rid of my mess. They don't really quite go away until I get to the horizontal, which is pi over 2. What do you think? Is everybody on board with that? Does that look right? Oh, you don't trust me. I make mistakes. All right. So, cool. 0 to pi over 2. Phi 0 to pi over 2. Okay, then finally, we're going to pick a value of phi. There is a phi slice of our theta slice, and we have to look at rho. Let's not lose sight of the fact that where that came from, this is sort of the disadvantage of redrawing as we just described there. Don't forget, it came from the three-dimensional picture, right? And so the starting value of rho there, don't forget it's actually there, which is the origin. And so rho starts at 0. And then let's see here, we end here, which of course is really there. And wait a second, that point is on that sphere. Now we have a little bit of a work we're going to have to go to. That sphere, it's a sphere, a radius given, center given. You can write down the rectangular equation. We need the spherical equation. You play the game, go through the conversion process, right? Plug in the change of coordinates formulas. So there's some work to be done there, and I claim that if you look at that and go through that process, this is what you will get as the spherical equation of that sphere. Now, I know I say this a lot, but please make sure you can do that, right? That's an important, it's stuff we did a long time ago, but you're going to need to be able to do that to do these kinds of questions. Okay, and so that, again, we have to solve for rho, and that gives us our upper bound. Okay. All right, now before we move along, another little sort of interjection of advice. The picture is really important. Take your picture seriously. It's really unavoidably a critical part of the problem. Some students will make these little postage stamp sized pictures. It's very hard to see off of a postage stamp sized picture. Keep in mind there's a couple of purposes for your figure. One is it helps you figure the problem out. Of course, that's clearly. The other is your figure is one of a few different ways that you have of communicating what you understand on an exam. And that's the goal on an exam, right? We're looking to try to get at, okay, what does this student understand? And so, since a picture can, to some extent, do that, I'm not going to say the picture is literally worth points, because this is not an art class, and I can't, in good conscience, count off for, lack of artistic, chops. But I also am not going to not give students points when they've communicated relevant understanding in a figure. So whether we like it or not, a good figure is an opportunity to get points, because it's an opportunity to communicate understanding. So please do take your figures seriously. The postage stamp size figure is a bad idea. Make it nice and big. Think it through. Make it a nice, clear picture. Don't expect that you're going to be able to take the equations that are given and that your inner oracle is just going to you're just going to produce a perfect picture first time. No, I certainly don't. I go through a revise and redo process. Usually, my first shot at a figure is usually kind of bad. And then I look at my figure and I say, here's what I don't like about that figure, for whatever reason, and then I redo it and it becomes better. And every time I draw a better figure, I learn a little bit more about the shape in question, and that additional learning helps me draw an even better figure. So there's a bootstrapping phenomenon here, right? It's sort of a spiral upward, right? Every time you redo your figure, it should get a little bit better. So anyway, take that part seriously. Again, don't just draw one and make do with it. There's no need to do that. Oh, related note, don't forget you have scratch space on the exams, right? The last 2 pages of all my midterm exams, I put 2 full front and back pages of blank space for you to scratch, do with as you please. And that's a great place to do your sort of like warm up, draft figures. Okay. And then lastly, there's stuff to know about how to draw good figures. I have a couple of recordings on my miscellaneous topics playlist. It's everything that I know about mathematical figure drawing. I think my mathematical figure drawing is pretty respectable, right? I can't compete with computer graphics, but that's not the question, right? The question is not what can you do with a computer. The question is what can you do with a pen. And so anyway, there's stuff to know. I would encourage you to watch my videos. If you want to find other resources online, I'm not gonna compete with real artists who might also have cool tips and tricks. So whatever you want to do there, but again, make sure you learn techniques. There is stuff to know that will help. And also, this is not a knowledge thing. This is a chops thing. You got to have the skills, right? There's a difference between knowing how to make a layup in a basketball game and being able to make a layup in a basketball game, right? And again, there's no getting around the fact that, if you want to have good figures, you need to be able to do it. It's not good enough to just know in theory how to do it. So practice is the thing that makes that happen. And, there's no getting around it. So give yourselves plenty of practice. Okay, pausing before I go on. Yeah.
I just had a quick question regarding in cases where parts of the integral or just parts of the calculation can be let's say it's part of the single variable integral is just a quarter of a circle or something. Instead of computing it, if you just pointed to the geometric construction and then solved it that way, would you still get sufficient marks, or would you have to actually go through the algorithm of computing the
I guess I don't really quite understand the question. It sounds like there might be some key details there. Can you hang out for a second after class? And we can talk through the details. Yeah, I just don't quite get but it sounds like a very reasonable question. Okay, so moving along, I've got a couple more examples. This one here, just to kind of mix it up, here we have the center moved now over on the y-axis instead of the z-axis, and you might be thinking, okay, well, come on, same diff. It's still a sphere, same radius, still on an axis, still sort of sideswipes goes through the origin there, and it's probably going to look a lot like, but you got to keep in mind, spherical coordinates is not symmetric between the axes. The z-axis is special in spherical coordinates, right? So this is going to end up being significantly different. So here we go. Thinking about theta slices. Theta slices look kind of like this, and again, geometric appeal. There's just, you got to think about this geometrically. I claim that because this ball is entirely to the right of the XZ plane, 0 to pi are the only theta slices that will actually hit this ball. Anything before 0, anything after pi is going off into the negative y direction, and there's just nothing over there. And again, that's almost entirely a geometric appeal. Now, how to see this? Look, one thing you can do, I've recommended, you can, I've recommended in the past, you can buy a sack of oranges, right, at the store, and a knife. Be careful, don't hurt yourself. And just sit there and start cutting it up. Right? Stuff like that can be helpful. Maybe some Play-Doh, possibly, right? If you want to sort of start off on the process of visualizing by having some actual three-dimensional stuff to work with, perfectly reasonable. But ultimately, got to be able to see it geometrically. So there you go, 0 to pi for the theta bounds. Yeah. By the way, let's doff the cap to don't forget your stretching factor. Don't forget to put the spherical differentials in what I'm going to call the correct order. Okay. Let's see here. Okay, now looking at a given theta. Whoopsie, wrong color. A given theta slice, which I'm going to redraw as usual. Right, that theta slice. Going to be a disc kind of like that. A little smaller for some values of theta, a little bigger for other values of theta, but they're all discs, and they're all kind of tangent to the z-axis, all at the origin. So they are different, but they have some things in common. And so again, let's think about the values of phi. And easy to kind of get confused as to, wait a minute, what direction am I going and what are these values of phi as you cruise along? I find it more satisfying over here on this other picture. And we start, wrong one. We start straight up where phi is 0. And then we get phi slices all the way along until straight down at pi. So phi goes from 0 to pi. Everybody happy with that? Okay. And then the row game. What do we do with row? Well, we look at one of those slices. Okay, that's in fact going to be like a slice kind of like that. And let's see here. Row starts there, which is actually there, which is the origin. So we start at row equals 0. And row ends there, which is actually there, which is on the sphere, which again is, okay, well, we got to figure out the equation of that sphere. So again, that's annoying, right? But you can write that down in rectangular coordinates. You can then convert from rectangular to spherical. Again, I'm going to leave that as an exercise for y'all to do. And when you do that, this is what you end up with. And again, to find the upper bound, right, that upper bound comes from where you solve for rho in that equation, which I'd already inadvertently done. And there you go. You see, there's kind of a process for this, right? It's very algorithmic. It's very sort of mechanical. You just basically have to reinterpret what slices mean, appropriate to your coordinate system, and don't forget your stretching factor. Okay. All right. Okie dokie. And I have one last little quickie tip. This is just an art tip. So here we have a domain that ends up looking like this, and it's sort of... it's what I'm going to call an intersection. It's an intersection in the sense that we're looking for, there's sort of two requirements that have to be satisfied at once. I'm going to say it's the intersection of this, the interior of that sphere, with the exterior of that sphere. So it's a kind of an intersection. So I just want to use that as a language, convenient language. We're going to want to look at this intersection. We're going to want to take cross sections, theta cross sections of that intersection. And how do we take a cross section of an intersection? This is just a purely artistic point. I think this is really, really helpful. Let's take a moment to recognize that seems geometrically hard here. It's hard to draw the intersection. It kind of comes down this way a little bit, but if I draw it, it makes it look solid. But it has this kind of scoop taken out of the inside. It's hard to draw, right? Neat observation. A cross section of an intersection is the intersection of the individual cross sections. And it turns out that the individual cross sections are just a lot easier to draw. So in particular, if I want to look at the individual cross sections, okay. Here's one of those theta cross sections. And what happens when I take a theta cross section of color choices of this top ball? Well, that's just a ball. A theta slice of a ball is a half a disc. That's easy to draw. Effortless even to draw. What about the bottom thing here? This bottom ball, what does that cross section look like? Well, again, it's a half disc. There's nothing to it. Right? And now back up to our rule. I want to find a cross section of that intersection. I'm going to interpret instead as the intersection of these two individual cross sections. And the intersection of these individual cross sections is just, well, what's in one but not in the other, and easy to draw. So a lot easier to do it that way. Does that make sense? It's a purely artistic point. Now, yeah, there's details. Yeah, sure, go through and think about the slices, and there's another little cool equilateral triangle that comes up, and yeah, absolutely read those details, think it through, make sure you're good with those details. But I think that artistic point is worthwhile. Okay. All right. Moving along, so that's kind of part 2 of section 5.5. Part 3 is, I'm going to have to say, this is going to be one of these topics where among my tough choices of things to spend class time on, I kind of have to admit this doesn't really quite, I'm going to have to leave a lot of this for y'all to read through the details yourselves. It's basically just an observation that sometimes integrals are obviously zero. This is a really cool trick. It's very nice. Perhaps you remember this. This symmetry theorem here is not, I don't know, this doesn't come up all that much, but here and there, I suppose. But if you have an odd function, like so, on my symmetric domain, that, you know, when you flip it over the origin, it doesn't change. So negative a to a, integral 0. And the reason that the integral is 0, pretty straightforward. It's here's our picture, here's our symmetric domain, and odd means that whatever extent it's up there, it's down here. And I think you can see that this term in the Riemann sum and this term in the Riemann sum, because of the oddness, right? The oddness says that f of negative p is negative f of p. So because of that oddness, we have a minus sign. The green and the blue are negatives of each other, and they cancel in the summation. Now, in a class you may have taken before, this might have been presented as, well, there's sort of a positive area here, and this is kind of a negative area. This is hand-wavy tape that they like to do in Calc 1 and 2 classes. But we don't have to be hand-wavy. I mean, you can see it right there in the Riemann sums. These literally cancel the integral of 0. So all I want to point out is that you can do this in higher integrals as well. You don't have to look at that. This is just, if you want a trick for how to, a different way to prove this result, you can do it with a substitution, as it turns out. It's a side note. So in higher dimensions, the equivalent of sort of reflecting over the origin is reflecting over some line. And there's lots of different lines that you can reflect over. And we're going to have similar ideas. A function has odd symmetry over that line if you get a minus sign. If, you know, every time you reflect, you get a minus sign. It's just like single variable oddness, just kind of generalized. And again, we're going to have an idea of what does it mean for a region to be symmetric. Well, it means that when you flip it upside down, nothing happens. And exactly as you would hope, if you have an odd integrand on a symmetric domain, that integral is 0. No anti-differentiation, no slicing required, no anti-differentiation required. Just couple of cool observations. Oh, that's 0. You drop your pen, you walk away. This is a bonkers powerful theorem. Oh my God, I think it's one of the most underappreciated computational tools. I think this is a massively powerful. It comes up all the time, regular basis. I made a conservative estimate. I sat down and tried to, flash back to, remembering, the old days, when I was doing physics classes and stuff, and y'all are doing engineering classes, and I'm not going to be that different. Y'all have a lot of integrals in your future. And my back of the envelope, based on my memory, conservative estimate is that 20% of the integrals that I experienced in physics classes equal to 0 by symmetry. 20%. That's a lot. Right? So this is an opportunity for you to spare yourself 20% of the integration workload in your future. I think that's a big deal. Do be aware, this is a really important observation. You do have to have both conditions. Very often students will see a symmetric domain and get too excited and forget to check to see if the function's odd. We'll talk about that in a minute. Or vice versa. So you do have to have both conditions for this to work. And also, very important, it's got to be over the same line for both conditions. If your function is odd over one line, but your domain is symmetric over a different line, it doesn't work. There is no symmetry theorem. Crash and burn. Not even close. Right? So, very critical little, I don't want to call it an asterisk, but I mean, it's an easily overlooked requirement that leads to catastrophe. So do be careful about those. Okay, so again, you don't have to look at that proof there. I had to get just for hand-waving purposes. I mean, this is morally why it's true. You can see we have a symmetric domain here, at least if you'll forgive my artistic incompetence. The idea was this is supposed to be its own reflection over this line. And if the value of the function at the reflection and the value of the function at your original point, if those are always negatives of each other, then again, these two terms in the summation cancel and the whole thing disappears in a puff of smoke. So, morally equivalent reasons. Now let's get our hands dirty and look at this example. Here we have let's draw our picture. We've got this curve, which makes, by the way, all this curve plotting stuff that you learned back in Calc 1 classes. Make sure you're good to go with all of that. And I claim it looks approximately like this. And then we've got that curve, which of course is something like that. And our region D is what's bounded by those two curves, which is this region right here. And now I'm just going to make a geometric appeal. Symmetric. Now, for your consideration, on exams and on the next page, in fact, I'm going to write down the explicit list of rules of what you have to show, what you have to do in order to make an accepted symmetry argument in this class. And the punchline is you don't have to prove it is symmetric, but you do have to be right. Right? So you want to make sure that you think it through. If you want to think it through in relation to this particular one, here's a case to be made. You can take a look at that. But you don't have to make the case, but you might want to think through the case so you don't accidentally, make a claim that isn't true and have nothing to fall back on because everything you said is not true. So heads up on that. Let's see. Now I further claim that the integrand is odd. Now the way we show an integrand is odd, keep in mind, you show something as odd by plugging in the reflection and making sure you get a minus sign. So, okay, no problem. How do we determine what the formula is for the reflection here? Well, our symmetry that we cited for the domain is over the y-axis, reflecting over the y-axis puts a minus sign on the x-coordinate, right? Geometric appeal. Again, now you got to be able to see it from the geometry. Right? But there's our line. That's what it looks like to reflect over that line, and it makes the x-coordinate go negative of what it had been. The y-coordinate doesn't change at all. And what happens then when I put a reflection, namely if I put a minus sign on the x-coordinate, if I put that minus sign into here, that minus sign gets cubed, which remains minus. When I put it in there, nothing happens because it gets squared. That means that this term here is clearly odd, because when you reflect it, it gets a minus. Now let's look at this other term. This other term, when I put the minus into the x right there, well, minuses factor out of the sine function. Flashbacks to trig class, right? Make sure you're good with all your trig. Stuff like that just doesn't go away. It keeps being critical over and over again. So again, we get an extra minus sign as required. So this function is odd, and we win. We have an odd integrand on a symmetric domain, both over the same line. This integral is equal to 0 by symmetry. Is that cool? Okay, so now just to be clear on what your rules are, if you want to use symmetry in this course, you don't have to show all the... I showed a bunch of algebra here just in case students wanted to... If you don't believe my sort of hand waving sort of assertions there. If you want to see some tighter algebra, there it is for your possible interest. What you do have to do though, you do have to explicitly cite symmetry. You got to say symmetry if you're using symmetry. You can't just say, "Oh, this integral is equal to 0." You got to say symmetry. That's the reason you got to say symmetry. Okay, you have to explicitly say, and therefore it's 0, right? So you can't just point to an integral and say symmetry, smiley face, and walk away. That's spiking the football on the 2-yard line. No touchdown. Because you got to conclude 0. You have to explicitly indicate which line of symmetry you're using. You got to say it. In this previous one, you would have to say over the y-axis. Right? And the big one, you got to be right. Hopefully this is obvious, right? But if you claim that there is a symmetry argument for a certain that makes a certain integral 0, if there isn't, then what you're saying is just that it just doesn't work. And it doesn't really matter how close of a call it was because there is no such argument. The argument doesn't work. Right? And again, it's about the argument, not the conclusion. So there has to be a valid symmetry argument that over the line that you claim. So anyway, make sure that you double check when you're going to use a symmetry argument that you're actually right. So anyway, these are the 4 requirements. And as long as you do those 4 things, by the way, how easy it is. You just say integral equals 0 by symmetry over the y-axis. That's very little to have to write down. Right? And as long as that is correct, full credit. Okay. The very last thing that I'll say about this is it is a powerful technique. I'm a big believer, devoted practitioner, right? So I strongly encourage you to use symmetry arguments. Just be careful. Because if you claim symmetry and there is no such argument, then nothing you've written down is true, and I got nothing to give partial credit for. So you gotta be super careful, make sure that it actually works. Y'all have a good rest of your day. We'll see you later. We'll pick up here next time. Oh no, we'll have a test next time. We'll pick up here on Tuesday. Okay, see y'all later.